Dear students, in the last class I have explained an important derivation called the Lensmaker's formula, which relates the focal length of a lens, the refractive indices of the lens as well as the surrounding medium, and the radius of curvature. So based on that, we have few numericals, so we'll start solving them. So the first question number 7 of the study material: if f is 0.5 meter, what is the power of the lens? So that is the first option. So power is given by the reciprocal of the focal length, which is 1 by 0.5. So this is equal to 2 diopter. So power is in diopter only when the focal length is in meter, which is already given. Let's go for the second option. The radius of curvature of the faces of the double convex lenses are 10 centimeter and 15 centimeter. So radius of curvature R1 and R2 are given. So one is 10 centimeter, the other is 15 centimeter. Its focal length is 12 centimeter. So focal length is given as 12 centimeter. So what is the refractive index of the glass? So we have to find the value of Ng. So in the case of lens, sign conventions are important. So let's consider a convex lens, and this is the direction of the incident ray. And then for this particular surface, if I extend it like this, the center of curvature comes here, C1. So this will be R1, which is in the direction of the incident ray. So therefore R1 is positive. So this is the second surface, and if I extend it like this, for this second surface, the center of curvature will be somewhere here, C2, and this is the direction in which I have to measure the radius of curvature, which is R2, opposite of the incident ray. So therefore R2 is negative. So sign conventions are important, and based on this now we can find the refractive index of the glass. That is 1 by f is equal to n minus 1 into 1 by R1 minus 1 by R2. So 1 by focal length is in centimeter, radius of curvature is also in centimeter, so there won't be any problem regarding the value of n. So f is 12 here. 1 by 12 is equal to n minus 1 into 1 by 10 minus of this minus, so plus 1 by 15. So this is 1 by 12 n minus 1 into, so if I take LCM here, I will get 150. This is 150, and in the numerator this is 10 15 times and 15 10 times, I will get 25. And this 25 150 is 6 times here. So I will get 1 by 12. Let me write that here. So 1 by 12 is equal to n minus 1 into 1 by 6. This 6 twice. So therefore this is 0.5 is n minus 1. So therefore n is equal to 1.5. So that's the second option. Now let's see the third one. A convex lens has a focal length in air 20 centimeter in air, and what is the focal length in water? So that is the third part of the problem, so which I am going to write here. Focal length of the lens in air is given, which is 20 centimeter, and what is the focal length in water? So I have to find Fw. So refractive index of the water is given, which is 1.33, and refractive index of the glass is 1.5. So this is one of the important problem. So when focal length in air is given, I will write an equation which is 1 by Fa is equal to Ng minus 1 into 1 by R1 minus 1 by R2. So this is one of the equation, focal length in air, where Ng is the refractive index of the glass. And when immersed in water, so 1 by Fw is equal to Ng by Nw. Now I have to write the refractive index of the surrounding medium. Here the surrounding medium is air, so therefore in the denominator it's 1 here, okay. Ng by Nw minus 1 into 1 by R1 minus 1 by R2. So this is the second equation, and now we divide. On dividing we will get Fw by Fb. Fw by Fa is equal to Ng minus 1 into Ng by Nw minus 1. This term will get cancelled. So Fw I have to find. So let me substitute that here. So Fw by Fa. Fa is given 20 into Ng minus 1. So, Ng 1.5 minus 1 is 0.5 divided by 1.5 divided by 1.33 minus 1. So, Fw is equal to 20 into 0.5 is a 10, 10 by, so we will simplify that 1.5 divided by 1.33, 1.5 divided by 1.33. So, we will give you 1.1278 minus 1. So, that will be 10 by, the difference is a 0.1278. So, 10 divided by 0.1278 will give you 78.25 centimeter. So, that is the focal length of the lens in water. So, basically you have to write two equation, which is the lens maker's formula, and then divide the two equation, correct, because the radius of curvature will remain the same in air as well as in water. So, that is why those terms will get cancelled. And focal length in water is nearly 4 times the focal length in air. So, this is based on the theory. So, here nearly, okay, so therefore, we get focal length in air is 20, 4 times means it is nearly 80, and that is what we find here. The answer is nearest to 80. So, this is based on the theory. Focal length of the lens in water is always almost 4 times that in air. So, let us learn one more theory, that is combination of the lenses. Whenever we design optical instruments, okay, like telescope, microscope, then we have camera, periscope. So, in all these optical instrument, we do not use a single lens, because single lens has a lesser magnification. So, therefore, we use multiple lenses, 2 or more lenses. So, what is the advantage of using 2 or more lenses? Moment you use 2 or more lenses, the magnification is get multiplied. So, multiplication will give you a larger value than the addition, correct. So, that is why in all these optical instrument we use more than 2 lenses for larger magnification. So, therefore, when 2 lenses are combined, what happens to their effective focal length? What happens to their power? So, that is what the next topic, which is combination of the lenses. And for the combination purpose, I am going to consider 2 thin lenses. So, this is lens 1, this is lens 2, having focal length f1 and focal length f2. So, this is the common principal axis, and all the distances are measured from the point of contact of the lenses. Now, in yesterday, in the derivation of the lens maker's formula, so we have used a logic. The logic is this: in a lens there are 2 surfaces are there, correct? And whenever refraction takes place, first we have applied the refraction as first surface with assumption that there is no second surface. Remember that. Then refraction through the second surface takes place, correct? And then we get a final image. So, here also I am going to use almost the same logic, that is, whenever refraction takes place through 2 lenses together, first I will assume the absence of the second lens. In the absence of the second lens, let us consider a ray which is incident, first ray incident normally to the lens, and it passes straight without any deviation, because it passes through the optic center like this. In the absence of the second lens, another ray I am going to consider. This object is at a distance u, and it undergoes refraction because there is no second lens. It undergoes refraction and it forms an image I dash at a distance v dash. So, refer this. This is the image formed in the absence of the second lens. So what is the object distance? It is u. What is the image distance? It is v dash. What type of object? It's a real object. What type of image? A real image. What is the focal length? f1. So which is that equation that relates the focal length, object distance and the image distance? It is the lens formula. So for the first lens, minus 1 by u plus 1 by v is equal to 1 by f1, because that is what the formula which we use. This is the lens formula. Minus 1 by u plus 1 by v is equal to 1 by f1. So this is a real object and we get a real image in the absence of second lens. That is most important. But in the presence of the lens, the ray after falling here will not continue. So therefore, we don't get this image in reality, correct? So that is the temporary image which we have formed in the absence of the second lens. So we have to write dotted line. So now what happens here, once the ray falls on the second lens, it undergoes further refraction and then it bends and then it forms the final image I at a distance v from the point of contact. Now for the second lens L2, I dash acts as a virtual object, so that v dash becomes the virtual object distance. V is the final image, a real image, correct, at I. So for refraction through second lens, I dash is the object and I is the final image. So therefore, using the lens formula again, minus 1 by v dash, because now that acts object distance, plus 1 by v final image, and then the focal length of the second lens, which is 1 by f2. So this is the second equation, and when we add these two, equation 1 and 2, 1 and 2, this minus 1 by v dash and plus 1 by this should be v dash here, not 1 by v, so that should be v dash. So this will get cancelled, and what we get is minus 1 by u, which is here, plus 1 by v is equal to 1 by f1 plus 1 by f2. So remember, this should be v dash, because for refraction through the first lens, I dash is the real image, no, at a distance a v dash. So that's why it's a minus 1 by u plus 1 by v dash is equal to 1 by f1. And now for the second lens, I dash acts as the object, virtual object. That's why minus 1 by v dash plus 1 by v is equal to 1 by f2. So now what is this minus 1 by u plus 1 by v? So this is nothing but 1 by f. And this f is called focal length of the equivalent lens. Now these two lenses, if I just extend it, just check this, if I extend it, this acts like a single lens. So when two lenses are combined together, the entire combination behaves like a single lens. So just like if there are two vectors, I can replace it by a single vector. What do we call that single vector? It's called resultant. Similarly, these two lenses can be replaced by one single lens, and we call that as the equivalent lens. Therefore, here f is the focal length of the equivalent lens. Okay. What is f1, f2? Focal length of the individual lens. If there is a third lens, just add one more, plus 1 by f3 with the sign convention. Because if there is a concave lens, you have to use minus sign. If there is a convex lens, you have to use plus sign. So like this, we can go on adding depending on the number of lenses placed in contact. Okay. So therefore, f is always the focal length of the equivalent lens, which we can replace it with single lens. So instead of two lenses, I can use a single lens. So now, what is the relation for the power? 1 by f is nothing but equal to p, and 1 by f1 is nothing but p1 plus p2. So effective power of the combination is equal to sum of the power of the individual lenses. Reciprocal of the effective focal length is equal to sum of the reciprocal of the individual focal length. But here, effective power of the combination is equal to sum of the power of the individual lenses. Okay. So this is how we can find whenever lenses are placed in contact. So, this is another important derivation of this particular chapter. 4 derivation: 1, refraction through prism, refraction through curved surface, then a lens maker's formula, and then lenses in contact are 4 derivation, and definitely so one of the derivation will appear for the final examination. So, based on this we are going to solve one numerical right now. Okay, the question 8, a convex lens of focal length 0.24 meter and refractive index of the glass, which is 1.5, is completely immersed in water of refractive index 1.333. Find the change in the focal length. So, this is what we need to calculate. So, this is the focal length in air. We already solved one problem just now based on this. That is writing the expression for focal length in air, which is 1 by Fa is equal to Ng minus 1 into 1 by R1 minus 1 by R2. That is equation 1. And then 1 by Fw is equal to Ng by Nw minus 1 into 1 by R1 minus 1 by R2. And then divide the two equations. So, I will get 1 by 2 is equal to Fw by Fa is equal to Ng minus 1 by Ng by Nw minus 1, and Fw by Fa is a 0.24, correct. So, this is what lens, we will verify that it is a convex lens, okay, fine. So, that is yeah. So, it is a convex lens of focal length 0.24, fine. So, Fw by 0.24, which is equal to Ng minus 1, which is 1.5 minus 1, which is 0.5, divided by 1.5 divided by 1.333 minus 1. So, 0.5 divided by, so again we will calculate this ratio, which is 1.5 divided by 1.333, which is 1.125 minus 1, okay. So, which is 0.5 by 0.125, okay. So, which is 0.5 divided by 0.125 will be exactly 4. So, this will be 4. So, that is Fw. So, Fw is equal to 0.24 into 4. So, that will be 0.96 meter. But they have asked what is the change in the focal length. So, therefore, we have to find Fw minus Fa. So, which is 0.96 minus 0.24, which is 0.72 meter is the final answer, okay. So, hope you have understood. It is a similar problem, similar to the one which we solved it. Again, it is from the examination, okay. So, we will try one more numerical. So, which is question 10. Two convex lenses of focal length f1 is a 0.2 meter and f2 is a 0.3 meter are placed in contact. Find the focal length of the combination, I have to find f, and then calculate the power of the two lenses. So, I have to find the individual power and then of the combination. So this is what the question. So very easy question. So F1, F2 is given, find F. So relation is 1 by F is equal to 1 by F1 plus 1 by F2. So 1 by 0.2 plus 1 by 0.3. See, 1 by 0.2 is same as 10 by 2. 0.2 is multiply by 10 here, you will get correct. So 10 by 2. So this will be 10 by 3. So 10 by 2 is 5, 10 by 3 is 3.333. So you will get 8.3333 is the answer, which is 1 by F. But we wanted F, right? But 1 by F is nothing but power. So remember, so if you are calculating the power, then that will be 8.333. So what is 1 by 8.33? So 1 divided by 8.333 is 0.12. So therefore, the focal length of the combination is 0.12 meter and the effective power is 1 by F, which is 8.333 diopter. Okay. So now what is the individual power? So individual power is P1 is equal to 1 by F1 and P2 is equal to 1 by F2. 1 by 0.2, which is 5 diopter, and 1 by 0.3, which is 3.333 diopter. So again, it's a question from the previous exam, easy 5 marks question. So hope I have understood the today's derivation and the problems based on that. And the remaining topic of this particular chapter I am going to continue in the next class.